Hello YouTube. In this video we're going to approach the concept of a conditional probability and basically revisit what we mean by a probability being conditional upon prior events. And so let's consider the rule for finding probabilities of dependent events in the first place. We say that if two events A and B are dependent events, then the probability of A and B occurring is given by the formula P A and B, or the probability of A and B occurring. We can see that it's just the product of these two probabilities here, probability of A times probability of B. But as we recall, this probability right here, this is referred to as a conditional probability because it's saying that if these are dependent events, then the fact that A occurred is going to affect how B comes out. And so the way we interpret this probability of B given A is essentially we read this as the probability that B occurs given that A has already occurred. And so we're going to refer to this part of this formula here as the conditional part, or the conditional probability, because it occurs upon prior conditions that have already happened. Or that is to say, it'll occur basically dependent upon the fact that A happened in the first place, since they're dependent probabilities. And so what I'm interested in doing in this video is essentially solving for this part of this equation here. And because we know that probability of A and B is equal to the probability of A times the probability of B, given that A already happened, then what we could do is we could divide both sides of this equation here by the probability of A. And what ends up happening is we get a new representation of the very same formula, but we get our probabilities of A canceling out. And so isolating this, essentially we get a new general way of finding the probability of an event given that something else has already happened, which is a pretty profound thing to be able to do. And so we would say that the formula for conditional probabilities, and again, recall that a conditional probability is a probability that has this vertical bar in it, and it essentially is a probability that represents how likely something is to happen given that prior events have already occurred. So just as we said, solving for this probability of B given that A already occurred, we essentially get probability of both of them occurring simultaneously divided by the probability of A. And so one thing I do want to mention about this is that the order of A, you know what, let me rewrite of here. But the order of A and B when you rewrite it, of A and B switch. When rewriting. And essentially what I'm saying here is that when we come across now probabilities of, say, some event occurring given that prior events already happened, then what we're going to do is we're going to take the probability of A and B divided by the probability of A. But the real question becomes, okay, so which one do I divide by? And so people say, well, the order doesn't really matter here. Well, order does matter. And so what I'm going to say is that the probability of B happening after A already happens, basically when you rewrite this, it becomes the probability of A and B. And these two events should always be representative of the first thing that happened. The A comes first. So when we write this, remember that the order switches and that these two have the same event. So let's go ahead and take a look at a situation in which we could use a two-way table in order to, say, look at a conditional probability situation. So let's assume here that a quality control inspector checks for defective parts. And so we say that this table over here shows the result of the inspector's work. So what we're looking for is A, first of all, the probability that a defective part passes, and then B, what we're going to look at is the probability that a non-defective part fails. Okay? So the way we need to look at this, first of all, is this. For part A, we say probability that a defective part passes. Another way of saying this is the probability that it was already defective, but that it's passing, okay? In other words, probability that it passes given that it's already defective. So what we're going to write first of all is the probability that it passes given that it's already defective. So the first thing we want to do is represent our probability symbolically, because what we're going to do here is looking at this. Remember, this is like our B and then our A. When we rewrite this, what we're going to be doing is we're going to rewrite it into the probability that it's defective, okay, defective, and passes. Now, with respect to the probability that we write down here in the denominator, let's say passes, it would be the probability of whatever the first event is up here, and we say defective. Okay, so defective. So here are the probabilities we need to find. So in order to find them, here let's go ahead and take our table here, and come up with some totals first of all. We'll extend this. We'll find, we've got all our joint frequencies. Let's find our marginal frequencies. So we say total. It seems to me that of the defective parts, 3 of them passed, 450 of them that were non-defective passed. We would say that we have 453 that passed the test, okay? And total that failed, we had 47, okay? So a grand total, if we grab our calculators here, 453 plus 47, I think that's an even 500, but we're going to go ahead and inspect it here. We say 500. So 500 total. In terms of how many total defective there were 39 defective. Non-defective looks like there's 461. Of course, this adds up to 500. So it would be worth our time to actually go ahead and convert all of these to relative frequencies. And I suppose what we mean by this is we're going to take all of these values here and divide them by 500. So for instance here, we would say that the relative frequency here that it's defective is 3 divided by 500. We would get 0.006. So I'm going to fill these in here. We say 0.006. If we take 36 divided by 500, 36 divided by 500, we get 0.072, so 0.072. And then our grand total here, if we were to add these together to get our marginal relative frequency, I say plus 0.006, we get 0.078. And so we have 0.078. And forgive me, I should be writing pass and fail up here. We'll go defective and not defective for defective and not defective. We'll go D and ND. So taking 450 now divided by 500, we'll say 450 divided by 500, we would get 0.9, okay, 0.9 or 900, I suppose. And if we were to take 11 divided by 500, 11 divided by 500, we would get 0.022. So 0.022. Now we're going to take that 0.022 plus this 0.900, which should be 0.922. But one thing I know is that when I add this vertically here, it should add up to 100% of our stuff. We say this is our totals here, our margins. And so looking down here, we would say this adds up to 0.906. If we were to look at, let's take 1 minus 0.906, we get left over the 0.094 that we would have gotten had we added vertically here, 0.094. So with all these probabilities, essentially what we're going to be doing is this. We're going to say find the probability that it's defective and passes. So when you look for defective and pass, that's this guy right here. We would say that 0.006 would be its probability. So we say 0.006. What we're going to do is divide this by the percentage that are defective. And so we say, where are the percentage defective? Well, the probability is defective is this marginal relative frequency here, 0.078. So we're going to say 0.078. And so using our calculators, this is how this formula works. We just grab a calculator at this point. We say 0.006 divided by 0.078. We end up with about a 0.0769. So I'm going to write all those 0.0769-ish, which is equal to a 7.69% chance of occurring. So what we're looking at here is a situation where now I can tell you how likely it is that something happens given that something already happened by rewriting this and evaluating it. And to answer this question, we'd say, how likely is it that it actually passes the test given that it's defective? And the chances are pretty bad. It looks like this test already was catching a lot of the defective ones, failing them, and keeping a lot of the non-defective ones. So it seems pretty accurate. So the chances of you actually giving it a pass, given that it was defective, were very, very small by looking at the experimental data here. So part B, let's go ahead and take a look at part B using our two-way table over here. Part B says find the probability that a non-defective part fails. And so the way we want to rephrase this is kind of like the probability that something happens given that something already happened. So when they say that a non-defective part fails, this is already true. We say that's the non-defective part, that's already true. We want to find really the probability that it fails. So we're going to say the probability that it fails given that it is not defective. So again, the first thing we want to do is use our formula here to say probability of B given A is really the same as the probability of A and B over the probability of A. So probability of A and B here, in this case again, we need to switch these around. We say not defective and fails, okay? And we would say this would be over the probability of not defective given that not defective was kind of the quote-unquote first event that was true. So when we look at this here, we say, well, what is the probability that it's non-defective and failing? Here's our failing, here's our non-defective. Looks like this 0.022. So we get 0.022 probability of that occurring. Now the probability that it's not defective at all, looking at all of our not defectives here, we say that 92.2% of them were not defective, so 0.922. So when we divide this out, this looks like it's not going to be very big. 0.022 divided by 0.922, we get 0.0239, so approximately 0.0239. And as a percentage, we could say that's about a 2.39% chance of this happening. So again, we'd say, well, how likely is it that it fails given that it's actually a good one? It's really, really not good, because if it's a good one, we're very good at catching these. So when you look at these conditional probabilities, really, this kind of goes back to how we were calculating it before, saying we're really taking all of these joint relative frequencies and dividing it by the marginal relative frequency on the outside of either that row or that column. So by looking at these, we were using a formula this time for something that before we were just interpreting as, taking the individual relative frequencies and dividing by the row totals or the column totals. So for instance here, the probability that it fails, given that it's not defective, okay? We found this algebraically. If we were to say, really interpreting this, find the probability that a not defective part fails, we're saying just of all the not defective ones right here, okay, what's the likelihood that it fails? So we're taking this divided by this here. So that's what we use when it comes to finding conditional probabilities. We use that formula. Cheers.